Let's consider two masses, m1 and m2. The force of attraction between them due to gravitation is given by this equation. Now, think about two electric charges. The electrostatic force between the charges, negative Q1 and positive Q2, is given by this. At first, these might seem like completely different problems, but mathematically, they're surprisingly similar. Both follow an inverse square relation with the distance, r, between them. The constants involved might be different, but the mathematical function behind them is the same. And here's the cool part. Math doesn't know what the constants are. Let's say we already know how to find the potential energy for an inverse square law. Then we don't have to derive the solution for every new situation. Instead, we can transfer knowledge from one context to another, simplifying the vast universe of problems. Imagine a particle moving around a circle at a constant speed, v. The velocity vector is always tangent to the circle at every point. Therefore, a vector from the origin to the particle, which represents its position, is always perpendicular to the velocity vector. We know that the rate of change of the position vector, with respect to time, gives the velocity vector. At first glance, this might not seem surprising. But look closer, the rate of change of a vector is perpendicular to the vector itself. We can actually break the velocity vector into two parts, the speed v, and a direction, a unit vector that's perpendicular to the position vector. For simplicity, let's assume that the speed v equals the radius r in magnitude. Then, the differentiation of the position vector simply gives another vector of the same magnitude, but perpendicular to it. But do we even need this differential equation to figure out where the particle is at any time? Not really. Suppose the particle starts on the x-axis, at position x equals r. Let's say at time t, it's here. The distance it traveled along the curve, the arc length L, is simply the speed times time. If the angle subtended by the arc at the center is theta, then arc length can also be written as r times theta. From this, we can evaluate theta in terms of time t. And because we assumed v equals r, it simplifies neatly to theta equals t. Now, consider this right-angled triangle. The position vector can be expressed in terms of the x and y coordinates, given by the base and height of this triangle. This can also be represented using the unit vectors along the x and y-axis. And look at that. We've already found the solution to this differential equation without using calculus at all. Now, what if I asked you to find a function whose slope at any point is the function itself? Yes, you guessed it. It's the legendary e to the power x, where e is Euler's number. For any point x, the function's value is e to the power x. The slope, given by its derivative, is also e to the power x. But what if we have e to the power k times x, where k is a constant? Using the chain rule, we first differentiate with respect to kx, which gives back the same function. Then, differentiating kx with respect to x, which simply gives k. So the slope becomes k times e to the power kx. For example, if we have e to the power 2x, the slope is actually double its earlier value. And now comes the real fun part. What if k isn't a regular number? What if it's an imaginary number? Let's say k equals I, where I is the square root of -1. Well, nothing changes in how we treat it. A constant is a constant, real or imaginary. So, when we differentiate, it's still just I times the value of the function. Let's say we have a complex number, z equals x plus iy. We can represent this in the complex plane as a point, or better yet, as a position vector from the origin. In this plane, instead of using unit vectors like I hat and j hat, we use I to represent the component along the vertical axis, called the imaginary axis, and we leave real numbers as they are, to represent the component along the horizontal axis, called the real axis. Now here's something really interesting. What happens if we multiply z by I? It becomes minus y plus ix. Here, y lies along the negative x-axis, and x lies along the y-axis. Let's focus on these triangles. They are congruent, which means both these angles are the same. If we rotate the axes by that angle, they align with the complex numbers. This shows that z and iz are perpendicular to each other. Therefore, I times e to the power ix is perpendicular to e to the power ix. Let's rearrange these vectors a little bit. This seems really familiar, doesn't it? It is directly analogous to the case where one vector's rate of change is another vector that's perpendicular to it, just like what we saw in uniform circular motion. Therefore, using this mathematical similarity, we can say the solution to z is given by cos x, sine x. But here's the twist. Instead of representing this using separate unit vectors along the x and y axis, we're going to describe it using complex numbers. And there we have it, the legendary Euler's formula. Thanks for watching. If you enjoyed this video, don't forget to hit that subscribe button and join us for more exciting and interesting lessons just like this.